The next lesson in the prerequisite chapter is P4 factoring. This lesson will help us in graphing, it will help us in solving pretty much throughout the semester. We'll use common factors and we'll look at special polynomial forms. A common factor is simply a coefficient or variable that all terms have in common. We had this on our Algebra 2 review worksheet. Sometimes when you have something in common, you can factor it out, but there's still a bunch of terms left over. So let's take a look. In the first example, we have 4x squared plus 12. Now each term is separated by the addition or subtraction. So there are two terms in this polynomial. They both have a factor of 4 in common in both of the terms. If you take that to the outside, it's kind of like you're dividing it out of the terms, but then we have to see what's left over. If we factor 4 out of 4x squared, we'll have x squared left over. Plus, if we factor 4 out of 12, we'll have a 3 left over. Let's try the next one. 6x cubed minus 4x. In this case, notice we have a 6 and a 4 for our coefficients, so we could take a 2 as a factor out of those numbers. We have an x cubed and an x, so we could take an x out of both of the terms as well. Now remember, it's kind of like we're dividing, so if we take 6x cubed and factor out the 2x, 2 goes into 6 3 times, and x cubed divided by x, we would subtract their exponents and have 1 less, or x squared, left over. Minus, if we take 2x out of 4x, the x's would cancel altogether, and 2 goes into 4 2 times. In our next example, negative 4x squared plus 12x minus 16, now we have 3 terms to determine if we have a common factor. Taking a look at all 3 of the terms, I notice they're all multiples of 4. And the unique thing about this problem is our lead term has a negative in front of the coefficient of 4. You would want to factor that out as well for purposes of graphing. In this case, though, we're just factoring. If we take out a negative 4 out of all of those terms, sorry about that, we would have positive x squared left over for our first term. But then if we change the sign for the factor, the second term, we would end up with negative 3 times x. So 12, or negative 4 goes into 12, negative 3 times with that x. And then the constant is negative 16, but if we factor out the negative 4, we would have plus 4. And there's your common factor. In that last group, it looks kind of unique and it almost looks like there isn't really anything they have in common. But this is kind of a form of grouping, and something like this would come up when we look at factoring with an a value that isn't 1. So if we look at the products of terms, we have a product here plus another big product. Can you tell what they have in common? If you look at the parenthesis that's written first, they both have technically an x minus 2 in common. If we think about factoring that out of both of those terms, then in that first term, all that's left over is that 2x. And then we have that plus, get that x in there, here we go. And in that last group, we have that 3 left over. So you won't often see it in the original form that it's in, but when we do that a times c split to get b rule, that's kind of the process that you'd go through to get your final factored form. Next up are some special polynomial factored forms. So you'll definitely want to make sure to know the templates for a variety of different types of factoring. The first one is called the difference of two squares, u squared minus v squared. So your terms have to be perfect squares to use this model, and it only works for subtraction. The unique thing about this factor, even though there are only 2 terms in the subtraction problem, you'll have 2 factors that each have 2 terms in your final form. And you can split them up with taking the square root for the first term, and you can add the second term, and then take the square root and subtract the square root for that second term. It always works this way as long as you have 2 perfect squares. Over on the right, let's put that to the test. X squared minus 9. Anything that's squared is automatically guaranteed to be a perfect square, and 9 is also a perfect square. That can be rewritten as x squared minus 3 squared. If you have a difference of perfect squares, it's as simple as already just going right to your two parentheses. The x squared would split up into x times x, and then you could have a plus and a minus, and you can really write those in either order, and then 3 and 3. Just like that, it works out that easy. Now in the example next to it, we kind of run into a little bit of a roadblock. Slide that over here, because it doesn't technically look like they're perfect squares right away. We have 5m squared minus 45. Thinking about the option of that common factor, can you tell that a 5 could come out of both of those? And if we do that, we would have m squared minus 9 left over. And we just factored x squared minus 9, so m squared minus 9 would do the same thing. The m squared would split up into m, the 9 would split up into 3, one of them can be plus, and one of them can be minus. Make sure to include the 5 as the common factor out in front. Now in that last example, we again run into another roadblock with the addition. We have a perfect square for r squared, and 4 is even a perfect square. But because you have addition, we can't split this up into a product of smaller parts. The addition in the middle wouldn't allow us to do that. Therefore, even though they're perfect squares, this is not factorable. See if I can get that to fit there. There we go. Next up, we have the sum and difference of two cubes factored form. Now this is what we talked about in that Algebra 2 review worksheet that has like the template to follow. It's kind of tricky, but once you use this kind of template as a guide, I hope that you'll be confident in this factoring process. You can factor both the sum and the difference if you have two perfect cube values. Notice there's an addition one first and then a subtraction one right down below. If you recall from that review worksheet, we always have a little parenthesis and then a bigger parenthesis. Even though they're perfect cube values, they only factor into two parts. We don't end up with 3 parentheses here. When you have addition between the original problem, you start with addition in the smaller parenthesis. Then in the bigger parenthesis, you take that first term and you square whatever it is, but then the sign changes to subtraction. You take whatever the two terms are and you multiply them together, and that's what's next. And then it goes back to addition and you square that last term. Now you'll always have that small parenthesis and the big parenthesis, and this big parenthesis will never factor further. So this is not factorable no matter how much it looks like it could be. It will never factor any further than that quadratic term. The difference when it's subtraction is just a couple of things. If it's subtraction here, it starts off as subtraction in that smaller parenthesis. We still do the first term squared, but then the sign changes to plus. Guess what? Everything else stays the exact same. You then multiply the two terms together and you add that last term squared. So these are just kind of templates to follow in order to factor perfect cubes. The hard part for this is trying to figure out if something is a perfect cube, so you may want a calculator just as reference until you become familiar with some commonly used numbers. Our first example on the right, y cubed plus 729. Y cubed is going to be a perfect cube because it's raised to the third power, so we get away with that one pretty easily. But 729, we kind of have to think about what number could you multiply by itself 3 different times to equal 729. Well, if we think 9 times 9 is 81, and if you multiply 81 times 9 again, you get 729. That means this is both a perfect, or y cubed is a perfect cube, and so is 729. Thinking of the u cubed plus v cubed template, we know to factor this, we're going to have a little parenthesis and a big parenthesis. That's always the case. Since it's addition right away, it will be addition in that first parenthesis, just like that. Then we take the first term y and we square it. It becomes y squared. Now the definition then makes us go to minus for that second part. And then we multiply the terms together. Y times 9 is 9y. And then it sticks to plus, and we take that second term, which is 9, and square it, and we get 81. That little parenthesis and that big parenthesis are the factored form for y cubed plus 729. Moving on to that next example, kind of like up above, notice here we've got a common factor, or we have a factor out in front. We've got that 3 in front of the x cubed. So if we divide the 3 out by factoring, let's see what's left over. If we take 3 out of 3x cubed, we would have x cubed left over. And if we take 3 out of 192, 3 goes into 192 64 times. And I think we even had 64 on our review worksheet from last week. That's the same as 4 cubed. So this would become 3 on the outside, x cubed minus 4 cubed. Since it's now a difference of perfect cubes, we'll have our little parenthesis and our big parenthesis. And we start off with x minus 4, since it's minus in the original problem. Take that x, then square it, and then we change our sign in that middle to plus. Multiply 4 times x, and that's 4x. And then plus again, 4 squared is 16. Last but not least, make sure to bring that 3 down as your common factor. And there's the factored form for 3x cubed minus 192. We'll end the video with factoring trinomials that have binomial factors. This is a scenario where it doesn't really fit one of our templates up above, and maybe we don't have a common factor to try to work with. We'll start off when our x squared term only has a coefficient of 1. In class, we'll change that up and come up with some new methods to help us factor. But now let's look at x squared minus 7x plus 12. When the coefficient in front of x squared is plain 1, all we look at is the constant at the end, or that c value, positive 12. Now, numbers that multiply to get 12 would be 1 times 12, 2 times 6, and 3 times 4. We have lots of choices to pick from. Our goal is to pick the pair that will multiply to get positive 12 and then add to get that negative 7 for the b value in the middle. Looking at our choices, I don't think 1 and 12 are going to be super helpful. 2 and 6 are close, but they're not going to work either. I think if we make the 3 and the 4 both negative, they'll multiply to become positive 12, and then they'll add to get that negative 7. Once you find your pair of factors that work, it's kind of like up above where we can set up our 2 binomial factors, split the x squared up into x times x, and we'll have 1 parenthesis with the minus 3 and 1 with the minus 4. That would be the factored form for x squared minus 7x plus 12. You try the next one. Go ahead and pause the video and see if you can come up with the factored form of x squared plus 10x plus 25. Once you think you have it, press play and we'll see if we have a match. Hopefully you found this one to be manageable. Breaking down 25, really only a couple of options, 1 times 25 or 5 times 5. In order to get that 10 in the middle, 5 and 5 would be our go-to numbers. X plus 5 times x plus 5, or you can write it as x plus 5 quantity squared. Either method would work out just fine. Now our last example, we have x squared plus x minus 6. Should seem straightforward enough, but sometimes this one gets a little tricky. Let's see what we can do. Now we have a negative number to work with, negative 6. We have 1 and 6, and we have 2 and 3. So I guess we only have a couple of choices, don't we? The goal would be to get negative 6 when we multiply, but then that positive 1 in the middle when we add. This would be a 1 right there. So if we take a look at how to get positive 1, the 1 and 6 really aren't going to be helpful. But if we make 2 negative and 3 positive, that would give us x minus 2 times x plus 3. Multiplies to get negative 6 and adds to get positive 1. That'll be good for today. Tomorrow, like I said, we'll finish the notes for the factoring on the back.